All right. Good afternoon to all of you. Can you tell me whether I am audible to you? Am I audible? Not yet? Okay. You can hear. So we started to discuss angle modulation that day, which divided into two types, frequency modulation FM and phase modulation PM. We'll quickly start with the PM and then move on to FM today. What was our idea? To load our information onto the carrier, choosing a certain property of the carrier like frequency, phase, or amplitude. The idea is that we need to recover the original signal at the other end by unloading, which is called the demodulation. And so long as this modulation are linear, then no distortion will remain in the recovered signal. Okay, that was the ideal situation. We were expecting that. So we will look at the basic principles of PM now, phase modulation, which has become very important with respect to data communication or digital communication, because most of the digital systems nowadays operate with phase modulation combined with amplitude modulations. So in using standards like 64 QAM, that kind of digital modulations. So the basic concepts lie here under the analog modulation techniques. So let us define this. There is a word called phase deviation. Deviation is the change of phase with respect to a reference phase. So once you define a reference phase, then the difference between that instantaneous phase of the carrier and that reference phase we call phase deviation. Please ask questions at any time, right? Okay, so phase deviations are there. Okay. Let us say reference phase of the carrier is omega ct, and instantaneous phase of the carrier is alpha t. This is the difference, alpha t minus omega ct, which we call phase deviation. This is phase deviation at a given moment of time, right? Then defining modulation, if that instantaneous phase deviation of the carrier is proportional to the modulating signal voltage, then we can impart all variations of the modulating signal as phase deviations on the carrier. So that is the idea of PM. So this phase deviation must now be proportional to our modulating signal. And we need to introduce a proportionality constant here. Let us say proportionality constant is Kp. Then phase deviations need to be proportional to xt, and the deviations now become proportional with coefficient. Let me call it Kp. But can we call this? This is known as sensitivity of modulator. Modulator will be a circuit, and that circuit will have a certain sensitivity. Sometimes this is called sensitivity of phase modulator. That's why the P here to stand for phase. And unit wise, you can notice the sensitivity is theta over xt, and this will be in radians, this will be in volts. So that will be the unit. How many radians of phase deviation will be generated by your circuit per unit voltage change of the modulating signal. Now that's Kp, and that's why it's called sensitivity. Higher the value of Kp, more phase deviation per unit voltage change, so more sensitive to capture the changes of xt. Right? Then we can substitute it to our theta here in the carrier, and that results in generalized equation for phase modulated signal. Right? This is a generalized expression. Okay, moving forward. The phase deviation will vary from instant to instant, but there will be a maximum at one point of time. That maximum phase deviation is called the peak phase deviation. Peak phase deviation is the highest value of phase deviation, which happens when xt you will get peak phase deviation happening in the carrier. So our xt is a variable, and we need to consider its maximum like this, which will result in maximum of theta. That's peak phase deviation, and remember that definition. Right? Let us define this angle of the carrier. Overall angle, instantaneous phase angle. Some books will write it as alpha it. I will use just alpha, but sometimes they call it instantaneous phase angle alpha it. Right? So same as what I am saying as alpha t here. I for instantaneous. Right? Instantaneous means at the given instant of time. Then by definition, we know rate of change of phase of a sinusoidal waveform is angular frequency, omega. So this is the instantaneous angular frequency known as omega I, and which is 2π times Fi. So what can we call Fi? It's the instantaneous frequency of the modulated signal. So by differentiating alpha t, you can find instantaneous angular frequency or instantaneous frequency. The same equation is sometimes given in exponential form, like this. You write it as the real part of this real part of the exponential term here, so that you will be getting the cosine term. You will remove the sine term of e to the power j theta. It's just another way of writing, which is also written like this. Right? uh, which shows the carrier component here multiplied by the component resulting from the modulation. This stands for the real part. Well, that's just another form only. Right? Okay, then frequency modulation is definition wise, it's very similar. Therefore, we will quickly define that also. Here also, like in phase deviation, we define frequency deviation. How do we define? Instantaneous frequency minus the center frequency of the carrier. Instantaneous frequency minus the center frequency of the carrier. By definition, we could say it's Fi minus Ft. I'm using Fi for the instantaneous value of the frequency. By multiplying it with 2.5, you can get angular frequency deviation. Difference between the instantaneous angular frequency of the carrier and the reference angular frequency of the carrier. Let us define it as omega I minus omega C. This is the one we are going to modulate. So we want these angular frequency deviations to be proportional to our modulating signal voltage xt. So that instantaneous angular frequency will be changing in proportion to the variation of the modulating signal voltage. Okay, so we can define the FM like this. Say the instantaneous frequency deviation of the carrier is varied in proportion to the modulating signal voltage. Some books will define this as instantaneous angular frequency variation. So both are correct, right? You may define it as instantaneous angular frequency variation or instantaneous frequency variation. So Fi minus Fc difference should be proportional to modulating signal voltage xt. This is that other definition I included. And in fact, I am going to use this definition. Okay. Angular frequency wise, we will define phase modulation becomes easier. Okay, Hiruna reminds me that I did not start the recording. Yeah, thanks for reminding. Okay, I hope we did not miss much. Right?
Recording in progress.
Thank you, Hiruna, for all that. Right? Okay, so this definition I'm going to use. Omega I minus omega C is proportional to xt. Does introduce a proportionality constant here as kf now, f for frequency modulation, right? Like this. Introduce kf so that omega it can be written as kf times xt. So this kf times xt term, we call it delta omega. Change of angular frequency. Delta for the change, so change of angular frequency. I means instantaneous. And that will have a maximum change, which I'm going to write as delta of capital omega, which is called the peak angular frequency deviation. Peak angular frequency deviation. right? Then divide that, you will get peak frequency deviation, which I'm going to write as delta F here. Peak frequency deviation. Remember that also. Earlier we defined for the PM, we were defining peak phase deviation. Here we define peak frequency deviation, which is kf upon 25 multiplied by max peak value of xt. With respect to dimensions, you can notice here kf is omega I minus omega c divided by xt. So what will be the units? This will be radians per second. This will be volts. So units will be radians per volt per second. 1/second is hertz. So if you divide this by 25, if kf is divided by 25, what will be the units? Kf upon 25 units will be hertz per volt, isn't it? What does that mean? It means that for 1 volt change in the modulating signal, this many hertz of frequency deviation will be created by the modulator. Therefore, either this kf or kf over 25 is known as sensitivity. Here, this is the sensitivity defined with respect to angular frequency deviation. This is also in this unit. Some books will give the sensitivity in this unit. Again, notice that there are two ways people give the sensitivity. But either way, it defines the amount of deviation created per unit voltage of the modulating signal by your modulator circuit, right? Peak frequency deviation we already defined, difference between maximum frequency and the center frequency of the carrier, like this. And delta F is a very important parameter with the practice of FM. Usually the quality of the FM signal depends heavily on the peak frequency deviation you allocate to that signal. Let's start with this again. Divide by 25. So instantaneous frequency of the modulated signal could be given by this formula. But we know rate of change of phase of a sinusoidal waveform is angular frequency by definition. Dividing that by 25, it is instantaneous frequency of the modulated signal. And for that instantaneous frequency of the modulated signal, you can substitute from this equation now. Phase is now alpha t, overall phase. So substitute for FIT. We will get that. And we will integrate phase angle. Bandari is asking, sir, can you explain the two ways frequency sensitivity? Well, some people give the sensitivity of the so many hertz per volt or something like that. And some give the sensitivity as uh, not hertz per volt, but radians per second per volt. Right? So many radians per second per volt. But it's a matter of just multiplying by 2.5. So some authors give the sensitivity directly with respect to frequency, some give it directly with respect to angular frequency. Nothing much, right? It's a factor of 2.5 only. So be careful when you read the textbooks because the way they define may vary by this factor 2.5. Right? Okay, so let us integrate this because we are trying to get at alpha t. If we get alpha t, we will be able to write the overall equation of the FM signal. So multiply by 2.5 and integrate. Alpha t becomes 2.5c into t plus kf into integral of xt with respect to time. Like this. So I will use tau in order to make the integral separate. With the limit 0 to t, you can integrate x tau d tau to find this term. Now that we know alpha t, we can write the equation of the FM signal. We did not modulate the amplitude, so it remains the same. Carrier, new after modulation, the new angle will be alpha t, which we have found now. So let us substitute here. You get the FM equation. Now this is a general FM equation, generalized FM. Earlier we found generalized PM equation. Shall we put them together and compare? This is what we found just now. This is what we found under PM. Lot of similarity you can notice. Amplitudes being same, untouched, not modulated. You can see this term 25C, that's the carrier frequency, same carrier. And also you can notice the proportionality constants, Kp and Kx. And here is an integral. Here is direct signal. So that's the comparison, as you can see. Now what if I take my signal xt, modulating signal, and pass it through an integrator circuit. Say I take xt, send it through an integrator and get the integral xt signal. And if I take that integral and substitute here as xt into a phase modulator circuit, what will be the output? From this comparison, you could say, then the output will be FM. So if you have a phase modulator circuit, and instead of feeding xt directly as your modulating signal, you integrate xt and then feed that signal to the input of the phase modulator, you are getting an FM output from the phase modulator circuit. So this is a way that you can generate FM using a PM modulator. This circuit, the integrator circuit in practice, it's called the pre-distorter. because our X3 when integrated will be distorted. It will be distorted due to the integral. Distorted X3 is what we are substituting as the modulator input to the phase modulator. Now the phase modulator output will become FM. This method of generating FM we call indirect method because we are using a phase modulator to generate FM signal. Method is then known as indirect FM. But there are separate FM modulators if you want to. You can use them to generate FM directly. So later we will discuss there are two ways of generating FM, direct FM or direct method and the indirect method. Is this clear? By comparison of two equations, it's obvious that phase modulator can be used to generate FM with the distorted circuit installed. Understood? Okay. So in summary, when we take a sinusoidal waveform, this is the angle alpha t. Now we know that when you modulate the angle, you will be getting variations in this term theta t in two ways. What are the two ways? Phase modulation and frequency modulation. Modulation theta t is directly kp into xt. In frequency modulation, this theta t is kf into integral of xt. So this did not change. This also did not change reference phase angle. This is the part which is variable according to the modulating signal voltage. There are two ways that variable can be generated, either direct proportionality or proportionality with the integral. So that's how the FM and PM signals differ. Okay. Please stop me if anything is not clear, right? Now, let us define modulation index for FM. Let us use the notation beta for that. This is how it is defined. Peak frequency deviation, unit is hertz. This is the bandwidth of your information signal, bandwidth of modulating signal. It is also in hertz. So beta is unitless. Peak frequency deviation after modulation divided by frequency band occupied by your information signal before modulation. That's the definition. Okay? Let's see another form of writing this equation. This is what we already wrote. Can be written in exponential form like this. Real part of the e to the power omega ct plus kf into this whole term integral, because it's difficult for me to write all that. I will write this as at, right? It's a function of time, which I will call at. In other words, at is the pre-distorted audio signal. Pre-distorted audio signal. Sorry, pre-distorted modulating signal, right? This pre-distortion means it's integrated. So this could be even expanded by separating e to the power j omega c and e to the power kf/at. And e to the power j kf/at can be expanded in the form of 1 plus, assuming that kf/at is less than 1. So e to the power jx so you may write the exponential term in a series, and you get these terms, right? Series expansion. This is e to the power j omega ct. I directly copy here. This part is the series expansion of this term. Then you can multiply by e to the power j omega ct, which is cos omega ct plus j sine omega t here. Cos plus j sine. Then multiply into the brackets and get the real parts. Then you will end up with this kind of an expression, which is the series expanded form of FM signal. Now this one is exponential form of the FM signal. This is a generalized form. This is a generalized exponential form. This one is the series expanded form of the FM signal. So you can see there are multiple ways FM signal can be expressed. What is our assumption here in the series expansion? That kf/at is small. Right? If it is very small, you can knock off some of these higher order terms in the series and approximate it to a few terms so that you can call it narrowband FM, which I will explain in a moment. Right? Everything okay up to now? Okay. Now, so far we were discussing the generalized forms, actually 3 different forms we discussed. Let's make it more simple now. Assume that our modulating signal is just one single frequency tone. Okay? Then equations become more simple. So we are going to discuss single tone FM. Assume this is our modulating signal, like what we discussed in AM. We now take a single tone, AM cos omega mt, as modulating signal. Then omega I will be omega c plus kf into xt. Substitute for xt as AM cos omega mt. Peak frequency deviation is then kf AM divided by 2π. That's the unit, hertz per volt. Sorry, unit will be hertz here. Now this should be equal to derivative of alpha, isn't it? So to find alpha, you can integrate. Get the integral. Now before that, if you are to understand how the angular frequency varies here, dot omega I against time. Sorry. So you will have a fixed value omega c plus, then it will be increasing and decreasing like this. Angular frequency will be increasing and decreasing. This will be delta omega. Peak angular frequency deviation. So angular frequency will be deviating with respect to time here. Right? Same thing, if you like, you can plot the frequency wise as well. If you plot Fi against time, there will be Fc here. Center frequency, and frequency will be increasing and decreasing with time. And this is peak frequency deviation, delta F. So it will move up to Fc plus delta F. It will move down to Fc minus delta F. And this delta F is proportional to your modulating signal amplitude, because it's Kf into AM. Kf into AM. AM is amplitude of the modulating signal. Kf is the proportionality constant. So peak frequency deviation is proportional to the modulating signal amplitude. So try to understand frequency variations like this. Okay. So our integral here was, let us integrate. This will give us alpha. Integral will become sine omega mt, and the term will come with omega m as the denominator. Now, we define this as our modulation index. Let me write it here again. Two fives will cancel. Let's define beta f, delta f upon fm. Modulating signal bandwidth is directly the modulating signal frequency here because it is a single tone. So now this is beta f. So we know the angle now. We can write the FM equation, single tone FM equation. Substitute for alpha t. We get single tone FM given as the equation now like this. It's known as single tone FM equation. Okay. Simple example. Let's assume a modulating signal is a cosine wave like this with an amplitude of 4. Carrier is a wave like this with an amplitude of 1. Then according to that derivation, it is now written like this with modulation index of 4. This is beta. So amplitude of 1 and beta of 4. This is our xt. After modulation, xfmt will be like this. You can notice when with the positive peaks, higher rate of change here. Frequency has increased. With the negative peak, frequency has decreased by delta F. The frequency at this point is Fc plus delta F. Frequency at this point of time is Fc minus delta F. The blue waveform is the modulated one. When you look at that waveform on the spectrum analyzer, this is what you see. At the center, we have the carrier component. This right on top of that. We have the carrier component here. Just white, right? And this is the first pair of side frequencies. This one is at Fc plus Fm. This one is at Fc minus Fm. That is why it's called a pair. So first pair. This is the second pair. Of course, the amplitudes must be equal, although this modulator has a small issue, slight unequal amplitudes in the pair. But theoretically, the pair will have same magnitude, same separation from the carrier. So this will be Fc plus 2 delta F and Fc minus 2 delta F. 2 FM plus 3 FM plus 4 FM and 5 FM and 6 FM. From here to there, it's 6 times modulating signal frequency. Here also, it's 6 times modulating signal frequency. So very wide bandwidth, isn't it? And FM is a modulating signal frequency now, 12 times that. Had I modulated this tone using AM, what would have been the modulated signal bandwidth? 2 FM, right? We proved that earlier. For AM, if I did AM, this is the modulated signal bandwidth. Now, this is the modulated signal bandwidth with FM, which is 6 times higher. You can notice when the same audio tone is modulated on a carrier using FM, it consumes 6 times higher bandwidth than AM. Remember that, right? FM signal is bandwidth hungry. Takes about 6 times more bandwidth than a AM channel. To put it in a different way, you could have transmitted 6 different AM signals, information of 6 different AM signals within the bandwidth of 1 FM channel. Then why are we using FM at all? It's highly inefficient with respect to bandwidth utilization, isn't it? Why do you think is FM more popular than AM nowadays, when it is taking so much of bandwidth? Suggestions? I thought you studied that in previous semester, right? No, attenuation is one answer I get. Another answer I get is energy loss. Not really. Another answer I get is information not lost due to attenuation. With the AM or FM signal will attenuate, isn't it? Attenuation depends on the distance traveled and the frequency, not the modulation. One answer I'm getting is we can amplify the signal without distorting the information, so we can transmit long range. Again, little doubtful about that. Amir is saying, the audio quality is good. But within brackets, you say maybe, right? It's not maybe, audio quality is good. In fact, you are correct. You gave the correct answer. The main reason for the popularity of FM is the better quality of the audio. Okay. Easy to extract at the receiver. Another answer, no, because AM is more easy to extract than FM. So the correct answer is Omaya's answer, where the audio quality comparison between AM and FM quality-wise, FM gives superior quality of the demodulated signal. So we are going to sacrifice 6 times higher bandwidth for better quality. It's a trade-off, isn't it? Bandwidth is traded off for more quality. FM has that ability of being able to trade off bandwidth and get more quality, whereas AM has no such ability. It can't trade off quality and the bandwidth. It can increase the quality by increasing the modulation index, but the bandwidth will be the same. Right? Bandwidth cannot be traded off for quality in AM channels. Let's continue with that analysis of sinusoidal modulation. This is the equation we ended up earlier. For single tone FM, let us expand this as cos A plus B. I lost my pen. Give me a minute. No, I made it white, right? Okay, sorry. Let's say cos A plus cos B. Sorry, cos theta plus phi, right? It'll be cos theta cos phi minus, this is sin theta, sin phi. So you expand using trigonometry of cos theta plus phi. Then we can define, based on that, we can define 2 types. Okay, Pereira is asking what is the reason that FM has better quality in the first place. Okay. Let us discuss a little bit more on this theory. We are going to define narrow band FM and wide band FM. At that time, I will answer this, right? So you will get the answer soon. In fact, that is exactly what is on screen. 2 types of FM are possible. There's one type we can achieve mathematically, we will see in a moment. One called narrow band FM. Let us call it NBFM. And opposite is wide band FM, WBFM. What's the difference? In narrow band FM, you are using modulation index less than 0.2, very low modulation index. Wideband FM, your modulation index is larger than that. Right? Why are we defining 2 like this? Because it gives us different quality. Let me show you. Initially, let us analyze narrowband FM. I'm rewriting that equation. Remember when we use cos theta plus 5, we ended up with cos theta plus 5 minus sin theta sin phi expansion. In this, if beta f is very low, like less than 0.2, we can do an approximation here, cosine of a very low value. Here we have a sine of a very, can approximate to 1. We can approximate to theta. Sine theta approximated to theta. Theta radians, right? So let us approximate this term to 1, cos of a very low value, sine of a very low value, we will approximate to radian of that value. Then rewrite, we get this formula. Okay. Then from that, we can see, we can draw a comparison with the AM signal. Let me write the two signals now. This is AM. I'm sorry, I made a mistake. Single tone AM signal we derived earlier is written below. FM signal is written above. Just draw a comparison. Can you see the carrier component here? And can you see the two sideband components here? Two sin A, sin B. Here two cos A, cos B, identical. So they look very similar. Let us see the spectrum. Then we can understand the similarity better. So expand and get the spectrum. This is 2 sin A sin B expanded as cos A minus B minus cos A plus B. This is cos A minus B minus cos A plus B. Now frequency components are now separate. So you can plot the spectrum. You can see the carrier component. You can see the upper side frequency component. You can see the lower side frequency component, just like AM, isn't it? Exponential form, same thing can be written. But let me plot this one. Sorry. We'll have the carrier component with an amplitude of AC from this. Then upper side frequency, lower side frequency. This will be at FC plus FM. This will be at FC minus FM. And if I plot only the magnitude, each will be beta F AC upon 2. See, the bandwidth is 2 FM, just like an AM signal. Can you see the similarity with AM? Same bandwidth, only one pair of side frequencies are there. That's why we call it narrowband FM. And identical with the AM. In exponential form, let us write the same thing. Real part of AC e to the power j omega ct plus beta f sin omega mt, which you can break into two exponential terms. Give me 1 minute. Sorry for the disturbance. Okay, now we have e to the power x term, which we can identify that it is periodic with a period of 2 pi upon omega. Therefore, we may be able to write this as exponential Fourier series. Right? We may be able to write this term as a Fourier series. Assume that we are going to write this term as this Fourier series with coefficients. I'm going to use dn coefficients, and each term of the exponential Fourier series is e to the power jn omega mt, and varying from minus infinity to plus infinity. Then I will be able to substitute this Fourier series here. Why? Because it's a periodic term with a period of 2 pi upon omega. Shall we then use the exponential Fourier series to represent that term? We can calculate dn by definition. You have learned that part. So dn can be calculated by this equation by definition. Integrate. Usually these dn values are denoted by standard notation in FM called Jn beta. If I'll explain this in a moment. So the two terms e to the powers are combined like this. Omega mt I'm writing as x, so that we can integrate with respect to x. Now this becomes a standard mathematical integral, not related to telos, but in mathematics these are called Bessel coefficients. Bessel's coefficients. Which we can directly read from Bessel charts. So these values, dn values, we may be able to get from Bessel charts, provided that I know my modulation index, beta f. For that given beta f value, given modulation index, I can read all Jn values from Bessel coefficients charts. That way, finding out the spectrum will be easier. So let me, this is known as a Bessel function of the first kind of order n. Argument is this term, it's our modulation index. These are the Bessel coefficients. You can notice beta values plotted horizontally. That's your modulation index. And you get likewise for a given here. And you can read this J0, J1, J2, all these J coefficient values vertically. That way, that series expansion will be easy to calculate the amplitudes. Right? There's another way Bessel coefficients are given, like this, where this value is n. N could vary from 1, 2, 3, 4 likewise. And for different beta values, different modulation index values, J and beta values are given. So you can use these charts also. So either way, you can read the J and beta values from Bessel charts. Easy method is to use the chart like this. For betas, your modulation index values, in our case, we call it beta. They are here. And J0, J1, J2 values are directly read in the columns. For example, for a given value of beta, like modulation index of 5, or you can just read along this line, and each amplitude will be available. And Bessel coefficients have this kind of properties. They are symmetrical, which means they are real valued first place. And also they are symmetrical. J and beta is same as J minus and beta. For n is even, for n is odd, it will be a minus value. So certain properties are there. This is that same FM equation in exponential form, which we already did. We now replace this. Shall we replace this with the Fourier series? Like that. And Fourier coefficients we now calculated as J and beta with values. So the real part of AC into Fourier coefficients here. Write that way. You don't need to write real part now. You directly take the cosine of this as the real part. Because J and beta values are real, you can take them directly here. Now, this is another form of that FM signal. This is very useful when you are plotting the spectrum, because when n is varying for each pair of side frequencies, so when n is 1, it is the first pair of side frequencies. N equals to second pair of side frequencies. Likewise, for each pair of side frequencies, this amplitude is readily available from the Bessel coefficient charts. So plotting spectrum, this third form. So we have learned 3 different forms of writing FM, single tone FM equation. Let's have a break here. After the break, we will use these J and beta values to plot spectra. Let's meet in about 10 minutes. After that, we will plot the spectrum by reading the Bessel coefficient charts, right?
Recording stopped. Recording in progress.
Sir, you are muted, sir.
Forgot to unmute, right? Sorry about this. Let me explain it again, right? Right. So what I was explaining was that when you select a particular beta value from the chart and read horizontally, values less than 10%. Any J and beta value less than 10%, which means value less than 0.1 is considered as insignificant. So you can remove them. For 1.5, another example, values 0.06, 0.01, you can remove. Here 0.03 you can remove. Likewise, remember, although the Bessel function chart has more values, for FM plotting, we will neglect insignificant side frequencies, and by definition, if the amplitude is less than 10%, we can neglect. Okay. So going back there, for beta values like 0.25, this is almost AM, like narrow band here. And beta equals 1, you can see it's not narrow band now, it's having second pair of side frequencies because J2 it is significant, right? Beta equals 2 up to J3 it is significant. Likewise, now beta equals 5 is a popular figure because for practical transmissions we normally use beta equals 5 for broadcasting. And you can see up to J7, it is significant. Sorry, up to J6, right? J6. J7 is insignificant. Okay, so your spectrum will have multiple pair of side frequencies now. This is that rule, chain beta greater than 0.1 must be considered. Right? By observing this table, you can notice that if beta is very small, like narrowband, it's only one side frequency pair or first pair of side frequencies that are significant. Therefore, bandwidth is comparable with AM. It is 2FM. Right? But if n is higher than that, sorry, if beta is higher than that, let us say very large beta values like beta equals 10, 20, etc. Significant side frequency pairs will be same as the beta value. Number of significant pairs we will not be using very large beta anyway, because for very large beta, bandwidth is not practically possible. We will be using moderate beta values. This is for large beta values, right? Okay.
Recording in
Number of
progress.
significant side frequency pairs is same as beta. One pair of side frequencies occupy 2FM bandwidth. So if n pair of side frequencies are there, it will occupy 2n times FM bandwidth, 2n FM. So beta is delta F upon FM. If you substitute for beta, it will be approximately 2 delta F. I'm sorry, it's for the large beta, I'm sorry. This is for very large beta, I'm sorry, not the medium values here. This section, large values. Sorry about this. For this section of the table, large beta values, what I said is true. This is true. Now, for intermediate beta values, which is around here, right? Around here, these are called intermediate beta values. You notice that number of significant side frequency pairs will be 1 plus beta. Not beta, but 1 plus beta. Each pair is 2 FM bandwidth, therefore, this will occupy, substitute for n, 2 times 1 plus beta times FM. which is 2 times FM plus beta times FM. Beta is 2 delta F over FM. Therefore, this will cut off. You will get bandwidth 2 FM plus 2 delta F, which will be approximated to 2 delta F plus FM. So 2 times peak frequency deviation plus modulating signal frequency is the bandwidth. I think you studied this as the Carson's rule in previous semester, right? Okay, going back. Why it is called Carson rule? Because Carson observed that for this range of intermediate beta values, significant side frequencies will be 1 plus beta. For example, if it is 2, here you will find 0.03 is insignificant. Therefore, it is J0 is the carrier. Then this is first pair, second pair, third pair. So 3 pairs, which is 1 plus beta. Beta equals 2. Beta equals 2, and it will be 1 plus beta value. So that observation by Carson led us to a simple way of estimating bandwidth of FM signal. That's why this is called the Carson's rule for estimating the bandwidth of FM signal. I hope you studied the Carson rule in the previous semester, right? Did you? Oh, no, okay. Sorry, I thought you did as a simple estimation, but this, what we did now is the proof. So anyway, Carson's rule is a simple way of estimating the bandwidth. Actual method is you refer to the Bessel function charts, plot the spectrum and estimate the bandwidth. But Carson rule, because Carson observed this simple rule that for intermediate beta values, significant side frequency pairs will be equal to beta plus 1. We are now having this simple rule, which is very effective when estimating bandwidth practically. Let me give you 1 or 2 examples on the use here. FM broadcast signals that you normally listen to when you listen to the music. Those channels, they are called high fidelity audio basebands because they carry frequencies from 0 to 15 kilohertz. So good for the music broadcast or hi-fi broadcast. Hi-fi means high fidelity there. This is the standard. Right? Peak frequency deviation for such a broadcast is plus or minus 75 kilohertz. This is the standard value. Modulation index is a standard value 5. Channel spacing is 200 kilohertz in this band. Channel spacing means if you take one FM channel, next FM channel likewise. These carriers will be spaced by 200 kilohertz. Adjacent carriers, 200 kilohertz gap. That's the standard Sri Lanka is following. Then if I use this rule now for our Sri Lankan FM broadcasting system, substitute 75 here, substitute 15 kilohertz here for the music, then you estimate the bandwidth, right? Sorry, I have not substituted, isn't it? This is 75 plus 15, which is 90 into 2, 180 kilohertz bandwidth per channel. So one channel is allocated 180 bandwidth here, but channel spacing is 200. Why are we keeping little higher? Because we want this 10 kilohertz and this 10 kilohertz to be serving as the guard bands. Why we are putting guard bands? Because if there is any drift of the carrier of one operator, it will not affect the broadcast of the other operator. Plus, also keeping in mind that we neglected site frequencies less than 10%, but actually they are there in the sky. So that's another reason why guard band is kept between the channels. So for each channel, bandwidth is 180 kilohertz, and we leave 10 kilohertz guard band on either side, making it 200 kilohertz channel separation, right? Similarly, you have other systems which are called, by the way, this is wideband FM, right? Because it aim for the quality. But we have narrow band FMs implementation in the form of what we call professional mobile radio PMR systems. Under PMR, you have categories like DMR, Digital Mobile Radio Standard. They have 1, 2, 3 categories. DMR 3 is more advanced with trunking capability. This professional mobile radio, therefore, professional operations such as firefighters, military, police, ambulance services, they all need intercommunication. So they carry communication sets. Such communication systems are called professional mobile radio, sometimes known as PAMR also. And they are not for music transmission. They just want the voice. They just want the key information to be delivered. So you make them narrow band, right? You are not going for quality. You are going for minimum bandwidth. But for broadcasting, you need to broadcast music with high quality, or they are called high fidelity systems. Then we use wideband FM. So you may notice that these narrowband FM signals use beta values less than 0.2, right? And these are having beta values much higher. Now in this example, beta is 5. So higher beta, you get more quality, more bandwidth. Lower beta, less quality, operates in less bandwidth. This is what we call quality bandwidth trade-off, so that you can make different services available to different kind of users at different prices using FM. But in AM, you can't do that because you can't vary the quality that much. Maximum modulation index is 1 and you can't go beyond that. Here, there is no upper limit as such, provided that you are ready to give more and more bandwidth. You can keep on increasing beta and getting higher and higher quality. So that is the idea what we call quality bandwidth trade-off of FM, right? AM has, it's not possible to trade off the bandwidth for quality. You can also see how simple the Carson rule is now. You just need to know peak frequency deviation and the modulation signal bandwidth, then you can directly estimate overall bandwidth of the FM signal. Anything not clear, please ask now. If you are listening to radio, I don't know whether you have time to do that. This is the signal you are listening to in Sri Lanka. These are the standard values. Now those narrowband channels like police communications, military communication, they use 12.5 kilohertz per channel. per RF channel. Here you can see it's about 200 kilohertz per RF channel. So huge difference in the bandwidth. This one is basically known as Digital Mobile Radio Standard, DMR. Sri Lanka is using DMR now. Police and military, they use DMR systems. In other countries, firefighters, ambulance services, emergency response teams, they all use DMR. Let's do a small exercise. Assume that we are having a modulating signal, triangular shape. Period is given here. Peak voltage is given. And we are to draw the modulated signals. If that modulating signal is modulated in PM, and if that modulating signal is modulated in FM. How do we do that? Carrier frequency is also given. Easier one to draw is PM, right? Sorry, in this case FM, because our modulating signal is XT here. Voltage is increasing and decreasing like this. According to the voltage variations, frequency will be increasing and decreasing. So you corresponding to this point, you get the highest frequency, lowest frequency, again highest frequency likewise. Now, if I differentiate this, what will be the wave shape? Take the whole waveform and find the derivative. And this is plus slope. During this time, it will be negative slope, positive slope, negative slope, likewise. So derivative of xt is a square wave. If I take a modulating signal and differentiate it with respect to time, and then that signal, if I feed into a frequency modulator, what will be the output? According to our previous discussion, we know that if our previous discussion was if xt is taken, integrated, and then fed down to a phase modulator, you can get FM output, indirect method. And we can do it the other way. If the given waveform is differentiated and then fed into a frequency modulator, you can get PM out. Right? So these are the two ideas. Right? Get xt, integrate it, put into a phase modulator, you get FM output. Okay. If you get a modulating signal, differentiate it, find x dash t, put into a frequency modulator circuit, you can get PM out. So if I use this idea for my exercise here, we have triangular waveform. Derivative of that will be this square wave. Then putting this into a frequency modulator, this will increase the frequency to a high value. This will decrease the frequency to a low value. So you will get F1 up to this, you will get F2 up to this, likewise. This will be the PM signal now. Phase modulator will give out this waveform when you apply that FM, when you apply that triangular waveform to the input. right? Another exercise. If you are given a square wave, FM will be like this, and you differentiate this d by dt. You get this is when differentiated, upward jump here, downward jump here. So you get delta functions, upward and downwards. And put this into a FM signal, you will, FM modulator, you will find every time the jump happens, the pace will be 100 going through 180-degree change here. The pace changes will occur in each section here. That is the PM output. So for this same waveform, this will be the FM output. This will be the PM output. Right? Those two are just to illustrate our indirect methods. Okay, now that we know the principle of FM and PM also, and under FM we discussed narrowband, and we discussed why narrowband is very important, especially for professional mobile radio systems, because it saves the bandwidth, but gives the sufficient quality for the purpose, but not the best quality. So we have sacrificed quality to minimize the bandwidth in narrowband FM signals. Then we learned that in applications like FM broadcasting, hi-fi signals are to be sent. You can't sacrifice the quality, so you sacrifice the bandwidth. 6 times higher bandwidth you are sacrificing for one FM channel to achieve better receiving quality in the receiver. Okay, so that's a summary of what we discussed so far. Now, how do we generate? Now, we already discussed there is direct method of generating FM. There is indirect method of generating FM. So let me summarize like that first. Direct method, indirect method. In the direct method, you take a voltage controlled oscillator IC, VCO we call it, voltage controlled oscillator IC, apply your modulating signal as a control signal, then frequency will be varied according to the modulating signal variations. Indirect method, we learned that you take the signal, get the integral, that is pre-distortion, then apply it to the narrowband phase modulator circuit, you will get FM output. So both are available to generate FM. Now we have ICs directly for direct method, like this Max 2606 IC, where you can directly give your audio input as to the control input here, and the FM output will be directly available and sent to the antenna. So for short range systems, this kind of ICs are very popular. They use direct FM. What is the issue with the direct FM? These are VCOs, voltage controlled oscillators, voltage controlled oscillator ICs. They use tuned circuits. They don't use any crystals. Therefore, their frequency stability is poor. Center frequency may drift, poor stability. You can only use that within your home and small distances, but if you are going public, frequency stability is not good enough or not within specifications. Here in the indirect method, you can use crystal oscillators which are having much higher stability and can meet the broadcast kind of stability requirements. So indirect method is more popular most of the time, unless it's a very short range application. Is it clear what are the two methods, direct method, indirect method? Let us look at the first one. We are going to use PM signal equation here. To get narrowband FM, we are going to use narrowband PM first. So this is the phase modulated signal equation. And then this is expanding this in the form of cos theta plus 5. Okay. One question Bandar is asking, why the stability of signal changes? Can you explain it further? It was not clear. Okay, thanks. Stability means the ability of the oscillator circuit to maintain its output frequency constant. When you use LC circuits or RC circuits as your tuning references, they are not highly stable. Your output frequency of a LC oscillator or RC oscillator has a stability level such as plus or minus 10 parts per million. I'm giving approximate values, right? Around 10 parts per million. Parts per million means 1 million oscillations, one cycle may be in error. So 1 million operation means 1 megahertz. No? For 1 megahertz, there may be 1 hertz plus or minus error in such oscillators. But normal, these broadcast kind of frequencies are around 88 megahertz to 108 megahertz in Sri Lanka, isn't it? So let us say 100 megahertz. That means 100 parts. So 100 parts per 1 million, right? So this will be 100 into 10, which will be 1 kilohertz error, right? That is too much, because when you get the license for broadcasting, the Telecom Regulatory Commission will give you stability limits. You can't violate them, because in that case you will interfere with the adjacent channel. Typical crystal oscillators are having about plus or minus 1 parts per million accuracy, which is very good for going public or broadcasting. Right? This is the ability of crystals. This is the ability of RC or LC oscillators. Normal voltage controlled oscillator ICs, they are using RC or LC oscillators. Problem with the VCOs are that their stability is poor. Crystal oscillators, the problem is their controllability is poor, but stability is high. Controllability is poor. You can't vary the center frequency very much. So these are the two ends that we have. So this is the reason that when you take a VCO, voltage control oscillator, you can't expect a very high stability at the center frequency. It will be drifting plus or minus 10 ppm within that range. Hope it is clear, Bandara. Okay. So those are the practical points, because you need to get a license from the government in any country in order to transmit RF. That license is normally very strict. They will give your center frequency should be this, your stability should be within this limit, and your guard band should be like this. So all that is specified, and for that license you'll have to pay, and you will have to adhere to it. If you violate, there will be a legal issue, right? Normally what happens is, if you violate these license conditions, either your license will be revoked or you will have to pay fines to the government. Right? Mostly cancellation of the license, and they will take the equipment also. So all those issues are there. in practical transmissions, right? Okay, one word about this slide now, coming back to this. If we expand like this, we get a very simple idea here. You can notice that your, let us say, modulating signal xt is taken, and we studied DSBSC ring modulator earlier, put it into the ring with this minus a sine omega ct. I'm assuming that this is my oscillator. So multiply xt with this, you will get this term by multiplication. This is multiplier. So that term will be there, a times kp xt sine omega ct. To that, you will take this a cos omega ct here and add. What do we get? You get narrow band PM, right? Because this cos term is 1 for narrow band. This one sine term is not there. So kp xt into sine omega ct is the term here. That term is generated within that. AC cos omega ct is this term. And summing these two, you will get narrow band PM. You can notice how useful is the double sideband suppressed carrier modulator, which we call the ring modulator, because it can do the multiplication. So for generating narrowband FM, you can use the multiplication. This way, you can create a modulator circuit. Right? So if you pre-distort your audio like integrating, then you can make it a narrowband FM signal. This is narrowband PM, but with this pre-distort added, you can make it narrowband FM. So that's how you generate narrowband FM signals. And that ring modulator, although we discussed that DSBSC is not popular for broadcasting, but you can see its modulator is popular even in generating FM signals. Okay, I think time is up. I'm sorry, I took extra time also, 1 or 2 minutes. So thank you very much for attending. I will upload the session. Next time we'll be able to finish the FM section and move on to the PCM. Okay, thank you very much. Have a nice day.
Recording stopped.